Chemistry is mostly a conceptual science, but sometimes it's necessary to learn some facts. Learning the structures of amino acids is difficult for students approaching it for the first time. Let me show you some tricks that you can use to make that process easier. When drawing organic molecules, it's good practice to identify the longest zigzagging chain and perhaps draw that horizontally. There are two ways to draw a chain. One is zagging down and another is zigging up. Zagging or zigging seems to make no difference, but in practice it does if stereochemistry is involved. Let me illustrate that by drawing 4 points and overlaying an amino acid structure on that. If I draw the amino acid zagging down from the nitrogen to the carbon between the nitrogen and the carbonyl, then the stereochemistry of an L amino acid will always point back. On the other hand, if I zig up in my diagram, that stereochemistry has to be turned around. It will always point out. Now, when remembering amino acids, it helps a lot to begin in the same place. And then the peripheral worries go away a little bit. So if you can remember to draw alanine in this way, all that's necessary to turn alanine into another 18 genetically encoded amino acids is to add the correct side chain. That's all you've got to remember if you always start with this drawing. The one amino acid, of course, that we cannot use this basic framework for is glycine. Poor old glycine doesn't have a side chain. It's just a CH2 between the nitrogen and the carbonyl. Not too hard to remember, very easy to draw. Zag down from the NH, up against the carbonyl, CH2 in between. Let's start with the aliphatic amino acids then. What's the difference between alanine and valine? Well, for alanine, we just have a methyl substituent. For valine, we have isopropyl. What's the difference between valine and leucine? One CH2 group. If we move the isopropyl down by one methylene, we get leucine. What's the difference between leucine and isoleucine? In isoleucine, one methyl group on the isopropyl is moved upwards and is substituted on that methylene, giving a chiral center. I put my hand on my heart and I tell you, I find it really difficult to remember the chirality, but it is S. And it's an isomer, of course, of leucine, so you've just got to remember to move that methyl group up and put it in the S configuration. Proline, drawing the structure of proline, difficult first time, maybe. But remember, draw the alanine structure with the side chain zigging back, and then just connect the side chain to the nitrogen to give a secondary amine in a 5-membered ring, to give a pyrrolidine. There you have it, alanine, valine, leucine, and its isomer, isoleucine, and the only secondary amine amino acid that's genetically encoded is proline, where the nitrogen is in a pyrrolidine 5-membered ring. Okay, if we have the structures down, let's remember the abbreviations and the one-letter codes. Alanine, A, simple. Valine, V, not too much hard work. Leucine, Lu, L-E-U, makes sense. Isoleucine, I-L-E, isoleucine. Proline, P, pro. So let me check. I said alanine, ala, A, valine, val, B, leucine, lu, L, isoleucine, I-L-E, I, proline, P. Not too bad so far. Everything's logical. Some other amino acids might be logically named using some of those letters, but the aliphatic ones take priority, the simplest ones. What are the aromatic amino acids? It helps to remember there's 4 of them. Histidine is one because imidazole rings are aromatic. Phenylalanine is one. That's the simplest aromatic. Tyrosine is another, just like phenylalanine with the para-OH group. And tryptophan is the 4th. So in histidine, his, H, the imidazole is attached to the basic framework that we've decided on to draw our amino acids. The simplest aromatic amino acid is phenylalanine, Phe, F. P has already gone for proline, remember? That's just a phenyl group on that skeleton. Then tyrosine is just like Phe, Tyr, Y, para-OH, slightly acidic, and tryptophan. Tryptophan has an indole attached to that framework. 2 complications to remember. There are actually 2 positions because of tautomerization that the imidazole of histidine can be attached. Tautomerization, remember, makes the 2 nitrogens equivalent. It's not the one between the 2 nitrogens. It's one of the other 2 carbons. And for indole in tryptophan, it's not the position next to the nitrogen, the 2 position, it's the 3 position. That's indole. Isn't it strange that nature takes certain orientations of a heterocycle and attaches them right there and not the other one? Acidic amino acids, really just 2. You might count tyrosine, which we've already covered, vaguely acidic, but not as acidic as aspartic acid, ASP. So glutamic acid is GLU. Remember, GLY is glycine. So GLU, a CH2, and then the carboxylic acid. It's a homologue of ASP. And the 1-letter code abbreviation is E. D and E for the acidic amino acids. And their amide derivatives, side chain amide derivatives, are asparagine, ASN, 1-letter code N, and glutamine, GLN, 1-letter code Q. Go figure, it's Q. Okay, so 2 acidic amino acids and 2 amide derivatives from those. Other acidic amino acids include tyrosine with that phenolic OH. There are 3 basic amino acids. The most basic one is arginine, ARG, ARG, 1-letter code R. It consists of our basic framework and then 2 more carbons and then a guanidine group. If you can't draw a guanidine group, you really have to practice that. Second basic amino acid is lysine, LYS. Lysine is like arginine, but don't make a mistake there. It's got another carbon in the side chain before the amino group. Arginine has 3 carbons, then a guanidine. Lysine has 4 methylines, and then an amino group. Lys, LYS, 1-letter code K. Histidine, we've already covered. Histidine is a basic amino acid. His, 1-letter code H. Along the way, you might pick up interesting features of amino acids. It would be a shame if you didn't. Glutamic acid is a really interesting one. It's emitted in the synapses and transmits a signal from presynaptic to postsynaptic neurons. And when that signal reaches a certain threshold, then ion channels open up and the signal is transmitted. down the nerves. Glutamate, very important in neurochemistry. Let's start with our core framework and bundle all the sulfur-containing and the OH-containing amino acids together. Simplest one is serine. It's got the core framework, then OH. Ser, S-E-R, one letter code, S. Homologue of that with the chiral center is threonine. In threonine, one of the CH2s of the serine methylene is replaced with a methyl group. And the stereochemistry of that is R. Threonine, three-letter code, T-H-R, one-letter code, T. And then the sulfur amino acids. Well, cysteines, just like serine, but with an S in place of an O. Cysteine, cis, one-letter code, C. It's cysteine that gets oxidized and gives disulfide bonds which hold proteins and peptides in certain configurations. These wonderful arrangements called cysteine knots at the core of some proteins formed from SS bonds. Serine is a very important residue. It's easy to think that methionine might be just serine with a methyl group on the S. No. It's just like the relationship between arginine and lysine. They're homologues in a way. Methionine is our basic structure, a CH2 group, then an S, and then a methyl group. Met, methionine, one letter code, M. Now you notice in all these structures, I've drawn the nitrogen on the left. That's convention, not just for amino acids, but for peptides too. It's a convention that's often broken because in some diagrams it's just a little bit clumsy to draw the nitrogen on the left, but that's the best way to do it if you have a choice. So drawing the nitrogen on the left always puts the N terminus on the left and the C terminus on the right. N and C termini, easy. The first amino group and the last acid. Think N to C. Let's introduce a little bit of Greek because we have to label the atoms in amino acids. And the one that you can't do without learning is the carbon between the amino group and the carbonyl. That is C alpha. From C alpha, alpha, beta, gamma, delta, epsilon. We don't need much more than that. In the last video in this series, I explained a lot about angles. I won't spend too much time on it here. You must know the difference between a bond angle, which is formed by three atoms. It's the angle between the peripheral two and the central one, and a dihedral angle, which I explained before, is the angle formed by one plane, say atom AB, relative to a second plane, say C and D. Dihedral angles that involve a clockwise rotation to make the front side chain eclipse with the back one are positive, and if that rotation is anti-clockwise, they are negative. A little bit tricky to understand, that's why I did it in a separate video. Please go back and watch that one if you're confused. Now the dihedral angles in amino acids are actually very important because these dihedral angles define secondary structures in proteins and structures of peptides in solution. For instance, in an alpha helix, two dihedral angles are maintained all the way down the spiral. Let's see what they are. But first, we have to define them. The two important dihedral angles in amino acids are, firstly, that formed between the carbonyl on the N-terminus of an amino acid and a peptide, and the NH, that forms one plane, and the C-alpha and the CO, that forms the second plane. That dihedral is called phi angle along the C-alpha to CO bond, chi, C on a keyboard formatted for Greeks. The third angle to worry about in peptides and amino acids is a boring one, omega. That's the dihedral angle between the CO and the NH of the amide. It's boring because it's always 0 or 180. Now we're talking here about the angles formed for the main chain. These are not the same as the angles you might predict using priority rules. So for instance, even though in a carbonyl, in priority rules, oxygen takes priority over carbon, in amino acids and peptide nomenclature, we're following the main chain. So we're talking about cis and trans in terms of the main chain. And they correspond to omega 180 and omega 0. Why is the omega bond simply 0 or 180? If it's not that, it's strained, it's distorted, it's energetically elevated. Why? Because of resonance. We know that amides have a significant double bond character between the N and the C and displace electron density from the nitrogen to the oxygen. Therefore, the oxygen is quite basic compared with the nitrogen, and that's where protonation tends to occur. Note in this diagram, I've shown resonance forms for trans and resonance forms for cis. Resonance forms of amides are just thought of in terms of this simple representation. So in this one, I've got N-methyl acetamide, and I'm showing the trans form. But of course, you can show enol and keto forms of each resonance structure. And note, the arrows are different. For resonance, we need a double-headed arrow. For the equilibrium between trans and cis forms, we need an equilibrium sign. Why is it that in most peptides and proteins, nearly uniformly, the amide bonds are trans? Because when we loop two peptides around in a cis conformation, we get ugly steric interaction between two groups. But in the trans conformation, that doesn't occur. For stereoelectronic reasons, steric and electronic, cis amides in peptides and proteins are far rarer than trans amides. Trans amides predominate. You can imagine in protein and peptide sequences, sometimes it's an advantage for the main chain to loop back on itself. And then a cis amide bond might be desirable. Nature has a plan for that. That funny amino acid, proline, pro-P. Well, of course, if you form cis and trans amide bond isomers of that one, corresponding to omega 0 and 180, the chain will loop back on itself, and in both cis and trans forms, there are steric interactions either way. Trans is still the most favorable, but cis is not so very different for proline. Nature uses proline residues, for instance, in beta turns or hairpins, where a peptide chain goes along like a hairpin and loops back on itself. Proline at the turns there. In fact, a very reliable way of making a turn is to use a combination of L and D proline, but that's beyond introductory organic chemistry. I have to tell you about pI values of amino acids too. pI values is just the combination of their pHs for the different residues. If we're talking about a free amino acid, the pI value will simply be the average of the amino and the acid pKa values, providing there's nothing acidic or basic in the side chain. Take the average of these two, for instance, and you get the pI value for alanine. Let's consider a basic amino acid, a little bit more complicated. So the way I conceptualize this is one amine and the acid will cancel each other out. And if the side chain is basic, like lysine, then the pI value is the average of the two basic groups. If the side chain is acidic, Like in aspartic acid or glutamic acid, the pi value is the average of the two acidic groups. Lysine is a basic amino acid because its pi value is greater than 7. Glutamic acid and aspartic acid are acidic amino acids because their pi values are less than 7. If you're a new student of organic chemistry, you may be thinking, what do I care about pi values? What use are they to anybody? Well, they're useful. Consider the surface of a protein. There we've only got amides in the main chain, but we've got side chains that could be acidic residues ionized to give you anions, or basic residues protonated to give cations. On a protein surface, we can calculate the electrostatic. In fact, chemists don't calculate anything these days. It's all black box. You just say, show the electrostatic surface. And we get patches of blue and patches of gray and patches of red. What do they mean? Lipophilic pockets formed from, for instance, aliphatic or aromatic are gray. Cationic pockets formed from the cations that we get by protonating basic amino acids at around about neutral pH are colored blue. Anionic pockets formed by deprotonating the side chains of acidic amino acids at neutral pH are red. If we imagine docking of ligands in pockets of these types, what ligands will be most suitable? Well, of course, for a lipophilic pocket, it will be a lipophilic ligand. Easy. What will it be for cationic pocket formed from basic amino acids? Well, it will be something negative, probably, due to electrostatics. And conversely, if we have a red pocket, that's an acidic residue pocket, anions, then the preferred ligand may well have a positive charge. The art of predicting or designing even ligands that fit in protein surfaces is extremely important in medicine, in biochemistry, and biology, for understanding, for instance, how proteins and proteins interact, or peptides and proteins, or small molecule drugs and proteins interact. Without understanding, acidic residues give negative pockets, basic residues give positive pockets, and lipophilic residues give lipophilic pockets. We can't really understand those areas. In this diagram, for instance, we have a big anionic pocket. I don't know what that ligand is. I didn't look carefully when I downloaded it, but I'm pretty sure it will have a positive charge to be attracted to that negative pocket by electrostatic forces. And of course, it will be the right shape to fit in there as well. There you have it. Those are the basics of amino acids. I've drifted a little bit into peptide chemistry, but we need to go that way very soon anyway. I hope this helps with your studies of chemistry and biology and biochemistry and what other biomedical science or biological science you're doing. These facts are ubiquitous in the life sciences. Thank you very much for listening. I really hope this helps. Bye-bye.
the bass, man.